So welcome, ladies and gentlemen, on this introduction about our new Elite Power Simulator. This work has been done by James Victory team, who is our modeling and simulation expert. And I have contributed in this team to make the tool, let's say, I hope so, more useful for you and in your day-to-day life. So here is the content of this presentation. We'll see why we have introduced a new tool and what are the objectives of this tool. And then we will compare the available tool and mainly two tools that can be used for simulation, SPICE or the system simulator PLECS. We will then dig in onsemi expertise in SPICE modeling and then go to the new tool structure and one we bring new to the system simulation. Why we have created this PLECS model generator and why we take into account component parasitic and see the effect of the losses and if it is important. We will talk about data density also, why it's important also, and after the conclusion I will do a brief overview of the tool and I will conclude and I will do a live demo after the conclusion. So let's see why we have introduced a new tool. We know with COVID and with our new way of living, we have more and more home office time or we spend more time working from home. And that's why virtual prototype has become more and more important and more important in the early phase of the design. From virtual prototyping, we expect accurate results. We need those to predict the system performance or behavior, to access information like junction temperature, node voltage inside the system information. We need also this virtual prototyping phase to be very accurate to avoid under or overestimate the system performances. And that will have an impact on size, on losses, on thermal, on mechanical design, and so on. We want, as onsemi, to bring you in this virtual prototyping to be closer to be what we call first pass to success, and to have and to avoid huge and difficult redesign after the first pass testing. Reducing testing time, because if you can test by simulation, you don't need to test by measurement at the end. Limit the test equipment, because if you can warranty features by design, it's better than test the feature at the end. And verify prototype behavior and performances by virtual prototyping. So the two tools that are available to simulate a system, let's say, we have SPICE and PLECS. SPICE is based on behavioral models that are been mainly created in the 80s to help AC design, and they are not made for power because, for example, they use lateral MOSFET, while in power we use vertical MOSFET, we use technology like trench, P-pillar, fill-stop layer, and so on, that are not modeled by behavioral model. SPICE need not very long time to simulate a three-phase system, motor drive, for example, or active front-end. I did one some years ago, and it took me 3 days of simulation to get a 5-line cycle. SPICE cannot handle multi-physics and handle only electrical variables. So for some variable, we use what we call thermo-electrical equivalence. For example, for thermal, where the power flow become a current and the temperature become a voltage. And in this way, we can predict the behavior of the thermal behavior. In the opposite, PLECS is a very fast simulator and can handle large system performances. It has already built-in multi-physics approach. And PLECS is based on table for switching event. This is what you see on the bottom of the screen, where you have a SPICE simulation and you have an accurate voltage and current simulation, and then you multiply the voltage and current to get the power, and you integrate the power to get the losses. In PLECS, it knows two status, on and off, And when it changed from on to off or on to off to on, it changed the voltage and current, and it plays like a Dirac function with the losses that he found in the table. So let's see now the unique expertise in onsemi that we call physical and scalable simulation modeling. So for simulation, for silicon carbide, it's even more important to use this technique that is based on simulation model containing a lot of equation inside the model based on the physics and the physics formula. So the input of this model is the technology. We have the cross section and the layout of the die. And we relate all those parameters like the doping of the end zone or the doping of the bottom layer, the size of each zone, the size of the gate, the size of the source, the size of the die, and so on. We include all of that as parameters. And through the equation, we can predict how the model works, how the device works. So for that, we also do a verification of our model in our Munich lab. And we can also bring you corner model, and we will see that in the future. And this is based on our statistical analysis in our manufacturing plant. If you can see on the extreme right, you have the schematic that is linked to the physical structure and the layout, and all the parameters inside those pseudo components, because it's not SPICE component inside, it's equation, are based on those parameters. You can see things on the bottom of the slide where you see the on region curve, that the slope of the curve change when the current increase. It's due to the fact that if the current increase, it generates more losses inside the MOSFET. And so we have more temperature increase, and so less capability, because the RDSO increase, less capability of conducting current. On the middle curve, you have the output capacitor, and you can see on the blue curve the CRSS that we can predict the sudden change of the CRSS linked to the fact that the depletion zone move from the epizone to the N+ region, and we have a sudden change of doping, and so a sudden change in capacitor value. But those models are not only made to make static measurement, they are made to be used in transient or in dynamic. And you can see on the on the right graph on the bottom, it's a turn on because the drain voltage goes down to 0 and the current increase. You can see that we can predict accurately the current spike at turn on. And also on the pink curve, you see the dip in the drain voltage due to the Miller plateau and the CRSS effect that generate a current that go in the gate. And that has to be absorbed. So if you want to know more about this modeling technique, you have I recommend you those 3 IEEE papers that are listed here. And if you want to use our model, you have all those documents available in onsemi website. There's documents that explain how we have obtained this modeling technique. There's documents that explain how to set up your simulator, Symmetrix, ORCAD, or EliteSiC, to use our model. And then you have example of characteristic extraction, like reproducing a datasheet. And you have also some example of system and things you can measure on a real application. So let's now look at the tool structure. So the tool we introduce is, in fact, a 2-in-1 solution. We have the left side and the right side. Let's begin with the right side, that is more common. You have on the right side a simulator, a PLECS Online license. And with this PLECS Online, you can take any devices, discrete or module, inside our EliteSiC portfolio, and simulate any topology, DC-DC, AC-DC, or DC-AC topology, and see what will be the performances like junction temperature, losses of the device, and so on. The new feature onsemi brings to PLECS or PLECS Online, because you can use this feature on both PLECS standalone on your own computer or on this PLECS Online. This is why you have this small arrow in the between of the two tools. The left side is based on our simulation capability that I have introduced, that you have seen. It's very accurate and include the real silicon carbide equation. It's not like a behavioral model that is based on silicon to try to reproduce how silicon carbide behave. We use those silicon carbide equations that we have extracted to generate the table that PLECS need to do the system simulation. And this generator is fully available online. And when you have generated the model, you can send that model directly to the PLECS Online or download the model, and we'll see that at the end of this seminar. Download that model to be used on your own computer. So why introducing the PLECS model generator? System level simulator like PLECS require those model or table for doing those very fast simulation, and they consider only two states, on and off, and in between, as I explained you at the beginning, they use the table to know what are the losses. Those model or table consist in three major characteristics: the conduction losses, the switching losses, and the thermal impedance data. So to obtain point, the simulator will either interpolate or extrapolate in this table to get the point in the middle and to get the value that he will use for the simulation. The problem is that when you want to generate such a table or such a model, you have two major, and either you use the datasheet, and in this case, if you see the datasheet, they are really poor in terms of number of value. Most of the time you have 1 million, sometimes you have a curve for the RDSO and so on, but you don't have so much point. The second way is by measurement, and if you want to do measurement in temperature, I did some in the past, it takes a long time, and you can spend 1 or 2 or 3 days to get value in temperature if you consider the time you need to stabilize the system. If you take half an hour or 1 hour to stabilize the system, to get 1 point, you need 1 hour. So onsemi came with a solution for that. It's based on our physical and scalable modeling that I have introduced, that is very accurate and contain already the SiC equation. We have included in that model generator the ability for you to describe the surrounding, what I call the surrounding. So what the quality of the switching inductor you are using, because when we do the datasheet, we try to use a very good inductor. You can include how many decoupling capacitor, the input filter, the loop inductance you have, and so on. And on top of that, by simulation, it's, let's say, nanosecond to change from one temperature to another temperature. So we can generate a large value in temperature that you cannot do in practice. And this will facilitate interpolation and extrapolation from PLECS. So why including parasitic component effect on losses? And is it really important? So here you see this is a double pulse tester, and on the inductor we use in our lab a very pure inductor. But in practice you cannot buy a very pure inductor, and you will have to accommodate to a real inductor that will have a parasitic capacitor, a parasitic ESR also. So here we are just focusing on the parasitic capacitor effect, and as you can see, at turn on, the more you have a parasitic capacitor on the inductor, it slows down the voltage drop and also increase somehow the reverse recovery. In fact, you have the reverse recovery plus the discharging current of this capacitor that appear inside the MOSFET and that create more losses. So if we look the ion versus this parasitic capacitor, as you can see, the ion increase, but the EF decrease. But anyway, when you have more capacitor, as you can see, you have seen on the slide before, you have more and more ringing, so more and more EMI that will be difficult to handle and to filter, and this is something you want also to avoid. And looking to a bulk stage and why we consider that, if you have the parasitic capacitor of a bulk stage on the inductor, due to the fact that we use large decoupling capacitor at the input and the output, this parasitic capacitor appear like in parallel to the switching MOSFET, and you can do the exercise for many topology. At the end, due to the decoupling capacitor, this capacitor will have an impact on the MOSFET and will appear like increasing the COSS of our devices. So next slide. So we have taken into account also the layout parasitic inductor. We all know as switching power expert that it's better to reduce the loop inductance, and this is why here we see that if we reduce the loop inductance, or if we increase the loop inductance, the ion decrease, but the EF increase, and we can see that there's an optimum here. We can guess for the total energy around 50 to 100 nanoamperes. If we get to that point, the total losses are somehow lower. But if you get to that point, I don't know if I have it on the next slide. No, I don't have it on the next slide. If you get to that point where you are in between 50 to 100 nanoamperes loop inductance, you will see that you're starting having a large EMI or large ringing on the waveform, and this is not good because you will have to increase the EMI filter that will impact the cost and size of your design. So it's better to keep it smaller. The decoupling capacitor, for example, at the end of the output filter, as you can see here, it has only an impact on ion. EF, it's relatively flat. And you can see that if you increase the decoupling capacitor, like in our double pulse tester in Munich, when we verify the model or verify the datasheet value, we have around 20 microfarad or even more. We have lower ion. But in your case, in your design, you can use perhaps 1 microfarad or 2 microfarad. Let's say I'm talking here about film capacitor and not chemical capacitor for high frequency, because they are not so good for high frequency. Here I'm talking of film capacitor for high frequency decoupling. You can see that 1, 2, or 4 microfarad is a good value, and 3 microfarad is a good compromise compared to the gain that you can obtain if you put 20 microfarad. So let's talk about data density, and I think I already started discussing about that. When PLECS make some interpolation or extrapolation, when he has 2 points and he needs the point in middle or in between or outside the 2 points, this is extrapolation, and in between it's interpolation. You can see if the curve is very nonlinear in between the 2 points, you will generate a large error. And the same with the extrapolation, if the curve is nonlinear between the 2 points and you're trying to see or guess what's going on above those 2 points, you can generate large error. While if you have a very large number of points, as you can see on the right side, when you do an extrapolation or an interpolation, you have much smaller data. And this is why we select in onsemi to have a large data set, is because it reduces the errors, and you have much more smaller errors in interpolation and extrapolation, and so you will have much more accurate results in your system simulation. So let's have a brief overview of the tool before I do a live demo at the end. So we have this PLECS model generator. that is a unique tool, and it creates the losses table for PLECS. We have seen that there's 4 major problems in that. The switching losses are dependent on parasitics and the measurement setup of the circuit. The conduction and switching losses are limited, and most of the time it's difficult to interpolate and extrapolate. Loss data are based on nominal process condition, and you don't know what's happened when the device is at the limit of the specification. And most of the time those data come from either measurement or the data sheet that are valid only for hard switching, and we are not able to predict what's going on with soft switching. With this new tool, the self-service PLECS model generator, we solve those 4 problems. And you can see here the link to access to this model generator, and it's completely free. So on the model generator, we have this complex or this detailed schematic where you can see there's a lot of parasitics or parameters that you can set. They are grouped in categories, and you have the input filter with the capacitor, the decoupling capacitor, the ESR, the ESL. You have the loop PCB inductance and the associated resistance. You have the drain and source PCB leakage inductance and resistor that is more due to the connection and the small tracks you need to go to the real source and drain. You have the series and parallel capacitor for the switching inductance. You have also damping networks between gate to source or drain to source, and you have a complete gate drive network to split the turn-on and turn-off resistance. I have to say that inside the device, and this is why if you look to the schematic for module, you will not see some of the parasitics. All the parasitics inside our package are already included. It means that if you take a TO247 compared to a D2 pack 7 lead, you will not have the same internal source inductance and drain inductance and so on. As the package in the D2 pack 7 is smaller, we have smaller parasitics inside the package. And this is already included, so you don't need to add extra value for the package. So when you generate a model, you input the range in between you want to generate the model in terms of you set the on and off voltage on the gate, you set the current range with the step, the diode current, the drain current, the switching current, and the steps. You set the bus voltage, the various bus voltage of your application, and also the various temperature where your system could operate. I would say it's taken also into account the first and third quadrant operation. And this is a list of the parasitics that we have included. You see there's more than 30 parameters. And here on that slide, you have some kind of, let's say, reasonable value for each parameters to be used inside the generator. But you can directly measure those parameters on an existing PCB or guess some value if you have work on design before, you know those value. And for the soft switching, we have been obliged to include extra parameters that we need, like the resonant inductor. Also, what is important for setting the energy store in the resonant inductor, it's not only the current, but also the DIDT. So that's why you have a new range to include the DIDT range and the step in this DIDT range that you want to generate your data. And you have the maximum delay or dead time between the turn off of one device and the turn on of the other device. This maximum delay or dead time works like an adaptive dead time. It means that if the dead time is smaller, the device will consider that the resonance is done and will stop the measurement inside the simulation. So with that, we can capture soft switching, but also partial soft switching when you have not enough energy to reach zero on the drain voltage and transfer all the energy inside the capacitor to the other capacitor. So this is some result of the effect of the EON and EOF for soft switching. You can see that for the EOF, we have a very small change in terms of EOF. The EOF remain almost the same or in the same range in terms of value, but for the EON, it's completely different. You have positive value in this yellow, orange, red zone. And when you are completely in soft switching and you see that it depends on the DIDT, you have this axis with the DIDT and the current inside the inductor, you turn completely negative. This is the purple or blue area where the energy stored in this output capacitor of the device is released inside the resonant energy and stored in the other device to turn off the other device. But in between, you have resistor that will generate losses, and this is why we can say during soft switching we have zero losses. Yes and no, because we always have resistor losses, and this is what we will capture through the parasitics inside this simulation to obtain the model. So the basic advantage of this Elite Power simulator, we generate a model with, let's say, we have a broad range of topology for DC-DC, AC-DC, DC-AC. We bring you corner simulation, meaning we give you the two extreme value and not only the average value. We can generate custom PLECS model with the parasitics. We can handle a soft switching in that simulator. You can get the loss and thermal data out, and it's very flexible. You will see you can run several simulations, compare them, and so on, and you have very fast and accurate result. For the topology available, you can see there's more than 30 topology. They are grouped inside automotive, industrial, and you have AC-DC, DC-DC, and DC-AC topology. For all those topology, by default, you have all SiC MOSFET discrete available, all 2, 4, and 6-pack module. We are working to introduce more. And as SiC product will be available, they will also be available in this model generator and in this topology simulator. So to conclude, I will say that onsemi bring a new online tool based on PLECS. This is not something really special, but with this unique feature, and this is the great thing about that tool, is this self-service PLECS model generator that is based on onsemi accurate and very unique physical and scalable spice modeling. We use this modeling with large table for better interpolation and extrapolation, as we have seen. And there's a direct connection with PLECS, either PLECS Online or PLECS Standalone. What you need to use this full online tool is just a MyOn login. You don't need any license, you just need a login in MyOn. All SiC portfolio will be available, diode, MOSFET, and module. We have the major topology available for single or three-phase AC-DC, PFC, active front-end, high power, non-isolated, and isolated DC-DC, and single and three-phase, 2 or 3 level DC-AC inverters. So the focus of the tool is really accuracy. And we don't want to give you up or unreachable result. We want to give you result closer to the reality. And this is why you can set parasitics and you can compare the result with your board. Or you don't set the parasitics and you get the default value, and this is something that already exists in our competitor. To generate the model, it's better to use a non-linear environment or a non-ideal environment to reflect your real application. That is more real than the double pulse tester that we use in Munich, and this is the environment that we use by default. If you take the default model for the system simulation, you will have our default environment. And for me, it doesn't make sense to take the default environment. It makes sense to take your board environment, your real number of decoupling capacitor, your real inductor with its parasitic capacitor, and your real layout with the length of the tracks and so on. For that, we have implemented more than 30 parameters to reflect those effects, and the tool can handle the hard and soft switching case and can generate models that are valid for the online simulator, and even partial soft switching is captured by the new platform. So this is link for accessing to the new tool. You have in fact two links, one for the self-service PLECS model generator and one for the Elite Power Simulator. And for each of them, you have a dedicated support email. So if you have questions, don't hesitate to submit those questions to those emails. So now it's time for the live demo. I will share my screen. So now you should see my screen. So when you come, let's go to the onsemi landing page. If you go to design, you will find the two tools here, self-service PLECS generator and Elite Power Simulator. So let's go here for the self-service PLECS generator first. You get to this landing page where you have the user guide of this tool, the application note that explains why we have introduced all those parasitics, and a link to our product table. And you have also some interesting white paper, and you have always the link between the two tools. This graphic explains you, and you can switch from one tool to the other one. And you have here the dedicated email. So let's start generating a model. So I need to log in. So it's very straightforward. You select the type of device you want to use, discrete or module. You select the technology. So let's take the last technology, the third generation MOSFET device. You select the voltage. For the moment, it's only the 1200 volt that are available. And I will use the, let's say, the 22 milliohm D-square pack 7-lead device. Then it's here that we bring one of our improvement is the process condition. You can use the nominal or average value, or the two extreme are linked. You cannot, you have the worst conduction losses, best case switching losses, or best conduction losses, worst case switching losses. Because if you increase or decrease the threshold, you somehow impact the switching losses and the conduction losses in the opposite way. And this is what we reflect here, and this is what we see also in our statistical analysis. Let's take the nominal for the example here. Here you can see the switching tip. You can select between hard and soft switching. So let's take the soft switching to see the improvement. Then here you have to set all those values. Sorry, it's a little bit long to set all those values. So I will start with minus 40 amps up to 40 amps with the step of, I can say 4 amp, for example, the diode 0 to 40 amp. with step of 4 amp. The current, let's say, well, I will start with minus 40, stop with 40 amps. I will, 40. I will step 2 amps to get a good resolution. Generally, minus 10 to plus 10 is most of the time enough. I will take 1 amp to have a good resolution. Here, I will probably set a smaller delay to see the partial soft switching. Keep the resonance, and here you set the voltage. So you just put a space in between, and the system recognizes the same with the temperature. Let's set some temperature, but you can set as many as you want to. So when you finish, you hit next. And this is where you set all the parameters like the gate driver, internal resistance, the propagation delay. You have the on, off, the min and max. So let's say I will use 2 ohm off and 5 ohm on to reduce EMI, and I will not go in detail in the other parasitic, but you can see that they are all zero, so meaning that they are not used. So this will speed up a little bit the simulation for the demo, the proposal of the demo. So then I submit the simulation request, and you get a summary here of the simulation. And so the simulation is pending and running. While the simulation is running, I will do an example on the power simulator, the system simulation, and then we'll come back to see what's going on here. So let's start. The page is really similar. You have the user guide of this tool, the application note, the access to our product, and some information here, why we did that. And same, you have the graph of the tool to see, you can move to another tool, some features, and the contact email here on the bottom of the page. So let's start simulate. So here I will choose industrial topology. I will choose, let's say, an active front end, 2-level 3-phase. You see the schematic appearing here. As my model is not generated, I will use the default here. So let's do VIN line to line. I will use the 400 volt AC and go to 800 volt. It's a more realistic case for a fast DC charger, 25 kilowatt, for example. And here I will use SiC discrete, and I will use the default value for the third generation MOSFET here. Let's say then here I will use 2 devices in parallel for that power. I will use a turn-on gate of 5 ohm, turn-off gate of 2 ohm. And here the same, I can use nominal data, base case conduction losses, worst case switching losses, or worst case switching conduction losses, base case switching losses. Or here, by clicking here this button, I will be able to upload the model I have generated in the self-service generator, the model that is running. But for the moment, we are using the default data, and here we can see we have a visualizer that you can see. We can see many. Let's go to the turn-off. It's easier to see. You see the various turn-off curve and the data density that you have. You see that we model quite well the device in the range of this operating range, 900 volt, 800 volt, 600 volt here. We have a good tracking of the values. And you see the data here in the table. Next step. So here we set the grid frequency, the switching frequency. We are doing a 6, so let's go for 75 kilohertz. We set the dead time in between, and next. Here on cooling, you can set the thermal interface, just RTH, or and the heatsink temperature, or you can customize the thermal impedance. You can either work with Foster or Coher network. And if you change a value, as you can see here, the curves automatically update, and you can add value for your Coher network. But here, for the example, we will just use fixed temperature. The advantage also of this tool is that it converts coher to Foster network and vice versa, up to 5 cells. So if you need that, you can use that tool, the tool for that. So let's run at fixed temperature. Then here we are on the simulation, and then I can simulate. So I just hit simulation. What's device parameters? I've taken what is your interface? I need to increase I need to decrease the inductor. So where is the inductor? Okay, here, because I'm running at high frequency, I didn't pay attention to that. Let's put that next, simulate. So the simulation is going. While the simulation is going, we can go back to the model generator, and you see that the model is done. So I can download the XML file corresponding to my simulation, and I can see the plots. And here, in this plot here, you have the E off, and you see that when you go negative, you move in soft switching, and you have only the resistive losses. You see the curve is like a parabolic curve, meaning this is the R on time square of the current, giving losses. And you see here those points on this axis capturing the partial soft switching. Here you have here many points. If we had a 3D curve, you will see that those points are captured like the plots I have. If you go on request for myself, as I'm onsemi, I see all onsemi requests. But if you go as a user, you will see only your example. And if you need, you can download the XML of this case. You can click to the case number to return back to the case. So if I hit this case, this is the case I have generated. I will return to that case and see the summary of that case. Or if I hit recall here on the right hand, I will recall that case to make a new case. And then you see that my system is already populated with the value I have used. And for example, if I want to generate one of the corner model, I just change here and go directly to the schematic and submit the request. And I would generate a new request by changing only one parameter. And that's much easier. So let's go back to the topology simulation. As you can see, we have now the value. We have all the waveform, the junction temperature, and so on. And one of the features that you have is to hold results here. So now if I hold result, those results are stored, and you have this result here. And then I can get here, for example, in somewhere and change some parameters, like if I run, for example, at 430, or let's use a smaller voltage to see the impact on the efficiency. And then I have to reselect my device. If you hit on the device name, you go to see the datasheet. I need to really click on the bottom to take the device. Next step, I will re-enter the values. So turn on 5 ohm, turn off 2 ohm. Next, I will re-enter. I think I use 50 and 0.2 here. Next, and then I can re-simulate. While simulating, let's go to this. No, I cannot go to the summary page. So we'll have to wait. Sorry. That is not taking too much time. You see that as I've decreased the input voltage, I see my input current increasing. So let's wait until the simulation is finished. You can see that for a three-phase active front end of PFC, the response time is quite good. In 1 or 2 minutes, we get the result. Okay, then I can also hit all the results. And you can see when I switch from one device here to the other device where I have changed the input voltage, I can see which curve correspond to and which data correspond to the result. And you can have features like having the table in by line or by column. You can download the value. You can mask some result. The same with the plot. You can enlarge the plot. And then you have a summary page where you can go. And here you have the two simulations that I have run with all detail that you can download or print as a CSV. But you can do also something like selecting the line you want and then hide the other line. And in the report you will get, you will have only the line that you have selected. So this is also a very useful feature when you don't want to have a lot of data on your final sheet and concentrate only on the data that you want. So this is all for today.